Hey everyone, welcome back to Calculus 2. This will be lecture 14 of the course. And so this is going to be a second lecture on differential equations. So in the previous session we talked about we introduced the idea of a differential equation and how it can be used to help generate a model. And we specifically looked at some examples of growth and decay models. And as part of that session, we discussed the technique of, the method of separation of variables when dealing with differential equations. And so in this section, we want to expand upon that further and develop a bit more rigor around what a differential equation solution is, and then do some examples, some kind of non-trivial examples of solving differential equations using separation of variables. Okay, so let's jump into it. We're going to call this section 2.6, differential equations and separation of variables. Okay, kind of a longish title there, but that's okay. All right. Okay, so the first thing we'll need to discuss is, what do we mean? And we kind of hinted at this last time, but more specifically and in more detail, what do we mean by a solution of a differential equation? So what do we mean by a solution of a diff EQ? Okay, so what does that mean, that word solution? So if we think back to algebraic equations, where you have maybe x squared plus 2x equals some number, 10, there's going to be some x that satisfies that equation. In fact, in the case of x squared, there'd be two of them, right? And we say that a certain number is a solution to an algebraic equation if, by plugging that number in to the equation is true, right? The equation basically you end up with a true statement. Okay, so just by way of making this really concrete. So if I have a simple equation like x plus 2 equals 5, this is very basic, right? But x equals 3 is a solution because 3 plus 2 equals 5 is true. Okay, whereas of course something different like x equals 4 is not a solution, right? Because 4 plus 2 equals 6, which is not equal to 5, right? So it's false, right? The same idea is we want, the same idea is true for differential equations, except solutions to differential equations are not numbers. Instead, they are equations themselves. So with a differential equation, it goes more like this. We say that y equals f of x is a solution of a differential equation. Okay, if the differential equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. Okay, so that's the idea. Okay, so in the case of the differential equation, a solution is itself an equation, and differentiating that equation and plugging y and its derivatives into the differential equations will satisfy the differential equations. Okay, so for example, y equals e to the negative 2x is a solution to y prime plus 2y equals 0. Right, so this is a differential equation, and this is a solution to this differential equation. Now, how do we know this is a solution? Well, first we come in here, we calculate y prime. So that's equal to the derivative of e to the negative 2x, right, which is negative 2e to the negative 2x. Okay. Then we can plug this into the diff EQ, right? So this guy plus this guy, when we plug it into this guy, ought to yield a true statement. So let's see here. So we have y prime plus 2y equals 0. So let's plug in y prime, which we just found is negative 2e to the negative 2x, plus 2 times y, which is e to the negative 2x. Okay, is this a true statement? Well, yeah, right? So this is negative 2e to the negative 2x, and this is 2e to the negative 2x. When you add them together, you get 0 equals 0. Okay, so, satisfies, that's what we mean by satisfies. It satisfies the differential equation. Okay, and so, in fact, we would say, so in fact, we would actually call y equals ce to the negative 2x the general solution of y prime plus 2y equals 0, right? So you'll notice this general includes this constant of integration. And so there would be other examples of solutions, particular solutions to this y prime plus 2y equals 0. This is just one of them. So y equals e to the negative 2x is a particular solution. Okay, whereas y equals ce to the negative 2x is a general solution. Okay, so so more on this in a moment. Actually, we'll come back to this in a moment. Okay, but basically the idea here is that there's a constant here of 1, right? If I had the equation y equals 100 e to the negative 2x, that would also satisfy this differential equation, right? And if I had any value, any real value for c would satisfy this differential equation, right? So you've got the particular solution, one of an infinite number, and then you've got the general solution, which is more like a form, right? A form of all of the solutions. Okay, excellent. Okay, and so that's what we mean by particular solution and general solution. Okay, a little more terminology, and again, this will be useful when you get to differential equations, the course. But this idea of the order of a differential equation, right? We've definitely seen this term order applied all over mathematics. It means one thing in algebra. It means something else in maybe linear algebra. It means something else in depending on which branch you're in. In abstract algebra, it means something different when you're talking about groups and whatnot. So in calculus or in differential equations, the idea of an order of a differential equation is determined by, it's basically a number that is determined by the highest order derivative in the equation. So the order of a differential equation is determined by the highest order derivative. Okay, so for example, y prime equals 4y is first order, right? Because it has a first derivative in it. Y double prime minus 3y equals 0 is second order, right? And this goes on and on. So first order, second order, etc. Okay. Okay, so let's do an example. Talk more about solutions here. Let's get more into the details of what are and are not solutions here. Okay, so I'm going to give you. We're going to write down 3 equations, and we're going to try to figure out which of the 3 is a solution to a particular differential equation. So which of the following functions are solutions to the differential equation y double prime minus y equals 0. Okay, so you got this nice differential equation here, and we're gonna lay out 3 examples here. So the first one will be y equals sine of x. Second one we'll test is y equals 4e to the negative x. And then the third one is y equals c e to the x. Okay, so which of these 3 is a solution? Right, so let's test the first one. Right, so in this is a second order differential equation. So that means we need the second derivative, potentially the first derivative as well. In this case, you don't need the first derivative, but you need up to the second derivative here. So we can calculate the derivatives really quickly. Y equals sine of x is the base function. The first derivative is y equals cosine of x. And then the second derivative is y equals negative sine of x, right? So keep those signs straight. Cosine differentiated becomes negative sine. Sine is positive cos. So those are the derivatives, and so all we need to do is test these inside the differential equation and identify one that satisfies it. Right, so y double prime minus y equals 0, right? Just plugging these derivatives in, we get negative sine of x minus sine of x. Minus sine of x equals 0. Right, so this would be negative sine of x minus sine of x, so this would be negative 2 sine of x equals 0, and so obviously that is false, right? Okay, in general. What about, you know what, I think this is actually supposed to be the first derivative here. Yeah, I think I just had a slight typo here. Yes, I did. Yep. So, sorry, so this would actually be y double prime minus y prime equals 0, and so this would be negative sine of x minus cosine of x equals 0, and so this would be negative sine of x minus cos x equals 0. So same result, though it's still a false statement. Okay, perfect. What about, so this one is not a solution. What about this one? What about y equals 4e to the negative x? Y equals 4e to the negative x, that's the base function, and then the first derivative of this function, right, would be y prime equals negative 4e to the negative x. Okay, and then the second derivative would be y double prime equals positive 4e to the negative x. Right, because see the negative here just keeps flipping the coefficient. Okay, so then we could plug this in. And so the second derivative is 4e to the negative x minus the first derivative, which is negative 4e to the negative x, equals 0. Is this a true statement? Nope. Here again, right, you're going to get, this will be 4 plus 4, right? So 8e to the negative x equals 0. False, right? So that's false. Okay. All right. And let's test that third option. My guess is that third time is a charm. So let's test that one. So y equals c e to the x power. And the first derivative, right, is the same, c e to the x power. That means the second derivative will be as well. All right, so all three derivatives are the same. So then it's rather obvious that y double prime minus y prime will be equal to 0, right? So plugging in the second derivative, you get c e to the x, and then minus the first derivative, which is c e to the x, equals 0. So you get 0 equals 0. True, right? So therefore, right, we would say that y equals c e to the x is a solution to y double prime minus y prime equals 0. Okay, and so it's just kind of that simple. Okay, and obviously there's, can be complexities. There are additional complexities there, with solutions and whatnot. But for our kind of preview of differential equations, that gives you enough, right? Enough to you can step away and say, oh, okay, a solution to a differential equation is another equation such that when I differentiate and plug it and its derivatives into the original differential equation, the differential equation is satisfied. Okay, I end up with a true statement. Okay. Okay. Let's see. Next up. So let's see. Particular solutions. Particular solutions to a differential equation can, so you kind of start, when you're solving differential equations, you sort of start by identifying the general solution, right? And then once you've done that, you can use additional information to identify particular solutions. So particular solutions are obtained typically from what are called initial conditions. So we saw this a bit in the previous lecture when we talked through growth and decay models. There we had a couple of examples where the example included some initial conditions like the population at a certain time, or perhaps the starting value of the population, something like that. And we were able to derive particular models, i.e. particular solutions to the differential equation. So these initial conditions will usually consist of two things. So these initial conditions will give you basically the value of the dependent variable, i.e. the y part of it. It'll give you the value of the dependent variable for a particular value of the independent variable. Okay, right. So they'll look like they can look like this. They can be as simple as y equals 10 when x equals 2. Right. So here x being the independent variable, y being the dependent variable. Frequently they'll look like this: y of 2 equals 10, rather. That's more common, I'd say. Right, so y being the dependent variable, x being the independent variable, and the value of y is 10 when x is equal to 2, right? So kind of a more concise way to write it. Okay, let's do an example of, where we take, a differential equation and a general solution and derive particular solutions. So let's say we've got s double prime of t equals negative 32. So this is our differential equation, and this has a general solution of, we'll say it's st equals negative 16t squared plus c1t plus c2. Right, so this actually is, from physics, this is like a position function, and this is going to be like an acceleration. Right, so this is a, kind of a common setup here. But let's say we have initial conditions. So this is the general solution, two initial conditions. Are, let's say, s of 0 equals 80 and s prime of 0 equals 64. Okay, so can we figure out what this differential equation is? Right, so what a particular solution would be. Okay, so this is the general solution. We need to know what basically C1 and C2 are. So to find a particular solution, we need to identify the values of C1 and C2. Okay, so this is all just algebra, really. Okay, this is all just algebra, but starting with s of t equals negative 16t squared plus c1t plus c2, we can figure out what the first derivative of this function is. Okay, so the first derivative of this would be negative 32t plus c1, right? Differentiating this. So just kind of think back to your differentiation rules if you can't recall, but this would be the first derivative of this general solution. All right, and so using this, we can plug in one of the general solutions, right? We can plug in this one, or one of the initial conditions, right? And so plugging that in, we'd see that s prime of 0, which is equal to negative 32 times 0 plus c1, needs to be equal to 64. Okay, and you can see kind of from this, we can force out that c1 is equal to 64. Okay. All right. Okay, and then the other one can be gotten from this, right? The other C2 can be found using this combined with the fact that we know that C1 is now 64. So S of 0, which is equal to negative 16 times 0 squared, plus C1, which is 64 times 0, plus C2 is equal to 80. Right, so this is kind of a straightforward example. This is 0, that's 0, right? So C2 must be equal to 80, right? So you've got the two constants identified now. And so given this as a general solution and given these initial conditions, we can derive a particular solution, right, that looks like what? Looks like, right, so given s of t equals negative 16t squared plus c1t plus c2 is a general solution, and c1 equals 64 and c2 equals 80, right, based on the initial conditions. right, we can derive the particular solution of what? So it's s of t equals negative 16t squared plus 64t plus 80. Okay, so that's the particular solution given the initial conditions. Okay, so that's a very common thing to be. It's a very common activity in the differential equations course, right? Initial conditions, right? So start with a differential equation, identify a general solution, use some initial conditions to identify a particular solution. Okay, it's very relatively straightforward, right? Usually the identification of the particular solution just involves plugging in some initial values and using algebra to sort of force out the value of the constants. Okay. All right. Let's do an example. Another example. Okay, so in this example, we want to verify that y equals c times x cubed is a general solution to differential equation. We'll call it xy prime minus 3y equals 0. Okay. Also find a particular solution, right, if the initial conditions of, let's see, y equals 2 when x equals negative 3 is given. That's an initial condition. Okay, all right, so there's the problem. So verify that y equals c times x cubed is a general solution to the differential equation xy prime minus 3y equals 0. Okay. Also find a particular solution if the initial condition of y equals 2 when x equals negative 3 is given. Okay. So in this one, we don't have to solve a differential equation. We just have to confirm that we have a general solution. That's something we've seen already. And we need to find a particular solution given this general solution. Okay, so we'll start by showing that this is a general solution. So y equals cx cubed. That implies that the derivative y prime equals 3c x squared. Okay, right. So that's the two pieces. We'll need this piece and this piece because we have a y and we have a y prime. Okay, so x y prime minus 3y equals 0. Okay, so let's plug in these pieces. So we have x times y prime, which is 3c x squared, minus 3 times y, which is cx cubed. And that needs to be equal to 0. Okay, and so we can see really quickly that that's going to be the case, right? So x times x squared is x cubed. Okay, so we've got that. Good. So we've confirmed that indeed y equals c times x cubed is a general solution. Now, can we find a particular solution? Okay, now find the particular solution. Okay, so given that given that y equals 2 when x equals negative 3. Okay. So we'll start with y equals cx cubed. Then we just plug in those values, right? So that means 2 equals c times negative 3 cubed And so that means 2 equals c times 27. And therefore, oh, sorry, that's a negative 27, right? And then that means c would therefore be negative 2 over 27. Okay. Okay, so that means the particular solution, well, a particular solution is y equals negative 2 over 27 times, all right, what's the general solution? X cubed. Okay, so that would be the particular solution. All right, very good. Okay, so that's enough on general solutions, particular solutions, and initial conditions, and all that stuff. Okay, so now what we want to do is we want to move on and sort of lay out kind of how separation of variables works. Okay, and then we'll do a few examples. Okay, so let's consider a differential equation that can be written as, and we'll do it like this: m of x plus n of y dy dx equals 0. Okay, so consider a differential equation can be written like this. So you've got m is a function of x alone, just x, and plus n as a function of y, just y, times dy dx equals 0. Right, so all of the terms are on one side. This is just 0 over here, and the y prime appears just on the just as a as a variable on the n of y term, right? So on this side of it, on this piece of it. Let me put that in there. So where m is a continuous function of x alone, and n is a continuous function of y alone. Okay. So in this example, this type of setup, basically for this type of equation, all of the x terms can be collected with d of x, and all of the y terms can be collected with d of y, right? So if you have it like this, m of x plus n of y dy dx equals 0, well, then it's a simple thing to subtract this term off of both sides, and you get m of x equals negative n of y dy dx. Then I can multiply both sides by dx, and I get m of x dx equals negative n of y dy. Right? And so remember, this is purely a function of x here. There's no y variables at all in this m function. And similarly, or likewise, n of y is purely a function of y. There are no x variables in this function at all. And so you can see that we have completely separated the two the two pieces here, right? So we have all the x terms collected on one side, all the y terms collected on the other side, and it would be a simple thing to integrate both sides, right, and to identify the solution in that way. Let's do some examples here, more real world, less like general. So what if I have x squared plus 3y dy dx equals 0? Well, yeah, this is exactly fits this setup, right? So your m of x is this piece, and your n of y is this piece, right? And so I could separate this. I could write this as 3y dy dx equals negative x squared, and then I could further write it as 3y dy equals negative x squared dx. Right, we could just do that. Okay. Another example. What about this? Y prime times the sine of x equals the cosine of x. Okay, so this one looks a little more complicated, not totally straightforward. But notice you could divide both sides by sine of x. And you'd get y prime equals cos x over sine of x, right, like so. And so then notice that, I mean, you can put this into that exact form, right? This, you could write this as cos x over sine x minus y prime equals 0, right? So here's your mx, and then your nx would just be like, you know, -1, or sorry, your n of y, right? And so this fits the form, doesn't it? Right, so it would be, you know, if you kind of did all of the work, you would end up with dy, 1 times dy equals, this is really the cotangent, isn't it? Yeah, so the cotangent of x times dx. Okay, so this, a little bit of work in between here. I just have to move some things around, but you can boil it down to this form. Okay, excellent. And one more example. These are kind of the sort of simple separation of variable types, differential equation examples, where you can kind of just do a little bit of algebra, like a little bit of algebra, and you sort of can get to the finish line. Here's another example. Let's say I have x times y prime over e to the y plus 1 equals 2. Okay, so I can divide both sides by x, and I have y prime over e to the y plus 1 equals 2 over x, right? And then just keep in mind that this y prime here is really dy dx, and so it's really 1 over e to the y plus 1 times dy dx equals 2 over x, right? So here's my m of x, here's my n of y, right? It kind of fits the format, right? I've got it, you know, I've got this on the wrong side. Well, just to make it concrete, if I had -2 over x plus 1 over e to the y plus 1 dy dx equals 0, then this would be my mx, this would be my n of y, right? And I would have the form m of x plus n of y dy dx equals 0, right? So that's the form you need, and if you do that, then you can see how it's separable. So 1 over e to the y plus 1 dy equals 2 over x dx, right? Then we can integrate both sides and solve this thing. Okay, right? So these are kind of the these are sort of like the examples that where, you know, it's relatively straightforward how to separate the variables out, right? So you get all the y's on one side, all the x's on the other. Right, so let's do an example where we kind of go from start to finish and actually solve the equation using kind of where the separation of variables is more straightforward. Okay, so let's find the general solution of, and let's say it's x squared plus 4 dy dx equals x y. Okay. Okay, so what can we do here? Well, we can divide both sides by x squared plus 4, and we could also divide both sides by 1 over y, right? So that would be sort of the first step. So let me actually kind of do it in 2 steps since we're learning here. Okay, so the first thing you could do is you could get this dy over dx equals x over y divided by x squared plus 4. Okay. Then the next thing you could do is you could get 1 over y dy dx equals x over x squared plus 4. Right, and so you can see I've got all of this is my n of y here, this is my m of x over here. Right, so it's separated, you know, it's pulled apart. Well, the last thing to do would be to move the dx out, right? So technically we would want this 1 over y dy equals x over x squared plus 4 times dx. Okay. Looks good. And then we would integrate both sides. Okay. Integrate both sides. And this one is straightforward. This is just the natural log, right? That one will be easy. This one will require u substitution. So let's set that up. So let u equal x squared plus 4. Then du is 2x dx. And so du over 2 should be x dx, right? So that's what we'll kind of need to do this one. Okay, so when we do that, we get, of course, the natural log of the absolute value of y. That's this guy. That's going to be equal to, let's write this as in the u terminology, so it'll be 1/2 times the integral of 1 over u du. And so we get the natural log of the absolute value of y equals 1/2 times the natural log of u, right, plus c1. We'll put a c1 there. And then substituting back in, we would get 1/2 times the natural log of u, which is x squared plus 4 plus c1. So this would be sort of like the general, this would be kind of like the general solution to this differential equation. Well, no, not quite actually. We're not there yet. We can do more to it. Let's clean it up a little bit more. Okay. So let me rewrite that one so I don't lose it. So we've got the natural log of the absolute value of y equals 1/2 times the natural log of x squared plus 4 plus c1. Okay, so let's take both sides and exponentiate here, right? So that would be, we have e to the ln of y equals e to the 1/2 ln of x squared plus 4 plus c1. And we can do a lot of things over here, right, with this sum. So over here we just end up with the absolute value of y, like e raised to the ln of something is just the something. Over here we can kind of mess around with this. We'd get e to the natural log of the square root of x squared plus 4. All right, that's bringing the 1/2 up here. And then plus c1. And then further we can do e to the ln of square root of x squared plus 4 times e to the c1. Right, so there's multiplication there. And then we can call this c. We talked about that in the previous lecture as well. So this would be c times e to the ln x squared plus 4. Okay, and then of course, I'm sorry, e to the ln, that one, maybe I should have done that straight away, but this is e to the raised to the natural log of something is the something, right? And so this would just be c times the square root of x squared plus 4, right? So that's the absolute value of y is equal to that. So this would be the general solution that we're after. And I guess, we could rewrite this as y equals plus or minus c times the square root of x squared plus 4. Now, and then technically this is plus or minus a constant, right? So actually we could even write this nicer and write it as y equals just c, right? Whether it's positive or negative doesn't matter. So c times the square root of x squared plus 4. So some constant times this square root. Okay, that's kind of the best way to write it. Okay, let's see, can we confirm that this is a solution to the differential equation? Yeah, so let's remember, what was our original differential equation? We had x squared plus y squared times y prime equals xy. So let's confirm that this is a general solution. Let's confirm that this is a general solution. Okay, so how do we do that? Well, we need the first derivative of this, right? So y prime of that is equal to c times d dx of x squared plus 4. That's the 1/2 power. And so that's going to be equal to c times 1/2 times x squared plus 4 to the negative 1/2, and then the derivative of the inside is 2x. And so we can write that as y prime equals c over x divided by the square root of x squared plus 4. Okay. Now what we can do is we can take this and plug them in over here. And when we do that, this differential equation needs to be satisfied. We ought to get a true statement. Okay, so let's do that. So to verify, we need to plug in y equals c times the square root of x squared plus 4, and y prime equals c times x over the square root of x squared plus 4 into x squared plus y squared times y prime equals xy. Okay, we need to test it. We got to test it in that differential equation. Okay, so we can do that. So we get x squared plus y squared times y prime, which is this. So it'd be times cx over the square root of x squared plus 4. Is that plus 4? Yeah. Is that? I gotta make sure I wrote it down right. I think I might have. Yeah, sorry, I did. Yeah. This is a 4. Sorry, I don't know where the squared came from either. That's a 4. Okay, very good. Good thing I checked that before I got too far into it. So we've got x squared plus 4 times cx over the square root of x squared plus 4. Right, so this is the y prime part. Just making sure we're tracking here. That's equal to x times y, and then y is, of course, this. So that's that part. All right. And then what happens here? Well, this is basically x squared plus 4 on the top, and this is x squared plus 4 to the 1/2 power on the bottom. So what do I end up with here? I can do some cancellation, and I end up with x squared plus 4 times cx equals, and then of course the same thing over here, isn't it? Cx times x squared plus 4, right? So we can see, that the equation is satisfied. Okay. Excellent. Excellent. All right. Good. Let's do another example. Examples are key, right? Throughout math. I do a lot of examples in these classes. I think that's just really the best way to learn, is to see the theory, right? See the theory. If there's a proof that's, at the level of the course, do the proof. Any derivation, of course, derive things, but then you don't want to leave out examples. Don't want to leave out examples, because that's really where you see how everything kind of fits together. Okay, so given that y of 0 equals 1, find the particular solution of the differential equation. And this is going to be x times y dx plus e to the negative x squared times y squared minus 1 dy equals 0. Okay, so that's kind of an ugly one. Okay, so let's write it down here. So x times y times dx plus e to the negative x squared times this quantity y squared minus 1 times dy equals 0. Okay, so this one is definitely not in the m of x plus n of y d y prime equals 0 format. This is definitely not in that format to start with, right? But let's see if we can maneuver it into that form. Okay, so the first thing we're going to do is multiply both sides by e to the x squared. Okay, and the reason we're doing that, of course, is we want to get rid of this x squared term in this guy and bring it over with this one. Okay, so when we do that, we have e to the x squared times xy dx plus e to the negative x squared y squared minus 1 dy equals, and then of course e to the x squared times 0 is just 0. All right, and so when we do that, of course, we get e to the x squared xy times dx plus, and then what happens over here? Well, this guy just disappears, right? And I have y squared minus 1 dy equals 0. Okay, so that's good. This is looking more about just, kind of just being wise. Then what we can do next is divide both sides by what? Y. We do the same thing, right? So we divide everything by y. That'll get rid of this. And of course, it's the 0 on the other side. That's not a problem. So 1 over y times e to the x squared xy dx plus y squared minus 1 dy equals 1 over y times 0, which is just 0. And we get e to the x squared times x dx plus y squared minus 1 over y dy equals 0. Okay, so there we can see that we do in fact have our mx over here and our ny over here. Okay, so that means the variables have been separated. All right, and so we can rewrite it, kind of move one of them over to the other side. And so when we do that, we would get this negative 1 plus y squared over y dy, so leaving the dy's on this side and moving the x e to the x squared onto the other side. Okay, and I changed the order here, right? It was y squared minus 1. I just made it minus 1 plus y squared. Okay, but not a problem. Right, and then we can clearly integrate both sides here, right? So you got an integral over here with respect to y, and over here you got an integral with respect to x, and all x variables, all y variables, so it's separated. Okay, so I'm going to integrate both sides. Okay, and so when I do that, I would have negative integral of 1 over y dy plus the integral of y squared over y, which is just y. Okay. Not too bad. And then the other side, I'm going to have to do a little bit more work to. This would be negative integral of x times e to the x squared dx. Right, so these two are straightforward. This one will require a u substitution. So let's let u equal x squared. Then du is equal to 2x dx. So that means du over 2 is x dx. Okay, and so we can handle that. And so let's rewrite here one more time. And then what are we going to do here? We're going to have negative 1/2 times the integral of e to the u du. Okay. Now everything is straightforward beyond this. So this would be negative natural log of y plus y squared over 2. Okay, and then over here this is negative 1/2 e to the u, and u is x squared. And then let's throw the constant on there. Okay. All right, so this would be kind of like the general solution, right? So it probably could be cleaned up a lot, but let's just plug in our initial condition and figure out what the the constant of integration here is, or what the c is. So the initial condition that's given is y of 0 equals 1, right? And so remember what that means, right? Y of 0 equals 1. That means y equals 1 when x equals 0. Okay, so we can just plug all of that in here. All right, so we get the negative natural log of 1 plus 1/2 of 1 squared equals negative 1/2 of e to the 0 squared plus c1. Okay, so basically this is 0 plus 1/2 equals negative 1/2 plus c1. Okay, and so a little bit of algebra, well, a little arithmetic at this point, it would just be that c1 is equal to 1, right? You got a half minus a negative half, right? So you bring it over. So c1 is 1. Then, we can crank out the particular solution. The particular solution is, we can write it as y squared over 2 minus the natural log of y equals negative 1/2 e to the x squared plus 1. Okay, so there we go. All right, very good. So that's a good example. Let's do one more example, and then we will break the video and have a part B, because this is well, let's just break the video now and have a part B. We'll go through one more example before we jump into the next topic. Okay.